Yesterday we assigned the Mendeleev lab of 1869. So I'm having students today check their homework. These are the unknowns, 1 to 7. Now the pattern you could have chosen would be the atomic radius. And you'll notice up here that lithium is larger as an element compared to, let's say, fluorine. So you kind of see that pattern there. The atomic radius increases down the group, focus on the metals, and it decreases across the period as you see above there. So this is a pattern that we've noticed, and then you can group things based on that pattern. And you could also separate them by gases and solids, but this would really help you distinguish the groups. You can see there's a mass there. Or these are the diameters, correction. These are the diameters. I'm not sure the unit doesn't say. Okay, so one of our students did a nice try, but you can see here that the pattern, they didn't see that pattern as far as putting them over here, as you see over here. So if you notice on the board up here, I'm just talking briefly about Lauren's selection. And we want you to really pay attention to nature, because if you see patterns in nature, then you're more likely to be successful in the choices you make as far as designing and engineering. So specifically, if you look at DNA and the mechanisms they follow, they're very organized. So we're trying to mimic efficiency. Like the human body is much more efficient than an automobile, if you didn't know that. Like we consume food, all right, then we move around with that food. So where does most of the waste go for an automobile? Anybody know? No. Where is it lost? Where is the heat? Yeah, it's lost as heat on the engine. So if you go up and you touch the engine after you've been driving around and it's hot, that's basically wasted energy. Now it's very difficult to convert all of that to mechanical because the engine could explode. You get into like pressure cooker scenarios. Now the human body is the same way. Where do we waste our energy? Well, if you look at remember snakes, are snakes poikilothermic or homeothermic?
Some of these words. Biology 1 did not teach me these words.
Remember that word, poikilothermic? Are we poikilotherms or homeotherms?
Cannot read that.
We're not poikilotherms. A poikilotherm is like a corn snake.
Damn.
Right? Homeotherms, basically, they are like us, in which we maintain thermal homeostasis. That is, a body in balance. And is energy wasted in that process of keeping our energy at a certain temperature? Yeah, your body is maintained at a certain temperature. That's why I call it homeothermic.
Water trying to maintain our temperature.
Whereas a snake, a snake is going to adjust to the temperature of its surroundings. And the big point with this is that a snake eats a lot less than we do. A snake can eat like once a week.
One rat.
Yeah. Whereas if we ate once a week, eventually we would either die from what?
Malnutrition.
Malnutrition or starvation.
Yeah.
So malnutrition is not getting all the nutrients that you need, right? All right, so here we have the molecular structure for vitamin C. Right? Now, the question is, what happens to you if you're malnutrition and you're not getting enough vitamin C?
You get scurvy.
You raise your hand. What happens to you?
No, wait, that happens if you eat too many oranges, right?
Okay, Claire, that's close. How about Eliza? If you don't get enough vitamin C. No.
No, you get like...
your energy goes down.
Close, no.
If you eat too much?
No, if you don't get enough, like if you're not getting any vitamin C, I don't think you'll die from a lack of vitamin C. But it will have an effect on your health. What will it specifically do?
It can cause you to be tired all day and zap your energy.
That's exactly what I just said.
Okay, so if you smile real quickly, if you don't get enough vitamin C, your gums will start to recede, and then your teeth, is that scurvy? Then your teeth will fall out.
So I was right.
Excellent, yes.
Or semi-metals. Metalloids have physical and chemical properties of both metals and non-metals. Silicon and germanium are two important metalloids used extensively in computer chips and solar cells. Silicon is also used to make prosthetics or in lifelike applications, as shown in Figure 6.6. The introduction to the periodic table touches only on the surface of its usefulness. You can refer to the Elements Handbook at the end of your textbook to learn more about the elements in various groups.
Okay, so the metalloids, if you turn back a page, you'll see the periodic table. So everybody see this? Turn page, one page back. You see the periodic table. The metalloids are found in what color? What color are the metalloids? Raise your hand. Points. 3 points. Raise your hand. Lauren? Green. The metalloids are green. Nice job, Lauren. Now, if you notice there, the metalloids separate what? Raise your hand. What do the metalloids separate?
The metals and non-metals.
Separate the metals and non-metals. Very good, Garrett.
They're semi-metals, so they're in between.
Yes.
Uh,
Yes, we're going to go with that just a second. But hold on. So we're talking about the difference between the metals and the non-metals, right? The greens. Everybody see this? This is the point we're trying to make to you. The metalloids. Talking about the metalloids. The metalloids are kind of like a blend of the two. They're a blend of the metals and the non-metals, and that they have similar characteristics. Now, what do metals like to do?
stay hard.
It's not great. Stabilize.
They like to do what with their electrons?
Oh,
Share them?
have an extra one.
No, metals trade, but what do they do with their electrons?
They,
Keep them.
they're
Gain the
They want to lose.
oh yeah, that's
Yeah. Metals want to lose electrons. That's what makes them metals. And then if you look at a battery, right? Batteries work because electrons can get lost, like your cell phone battery or your tablet. So because of metals and their desire to lose electrons, we can power our devices. Make sense?
Yeah.
Like the lithium. Lithium would be a metal. It's in group 1. Now the metalloids, they are kind of like hermaphrodites. Right? What's a hermaphrodite?
That is very nasty.
a woman and a male.
No, it's an earthworm. Like earthworms,
Okay, you're talking about that.
that's a hermaphrodite. Earthworms are hermaphrodites in that they have both male and female reproductive genitalia, right? So that's kind of what the metalloids are. Now, the transition metals are not hermaphrodites. Transition metals are metals that have multiple charges. So there's a big difference between a transition metal and a metalloid. Now, earthworms, they will change their, I guess you would say, reproductive type on a cycle. So they're on a cycle, like women have a cycle, earthworms have a cycle. And they cycle so that they don't do what? So they don't inbreed. Because all earthworms look the same, right? So they have to prevent themselves from, inbreeding. But the point is that the only reason why I bring that to your attention is that in our world, we see something similar to the metalloids. And in life, we tend to replicate what we're made of. We tend to have some of the characteristics of what we're made of. So we're gonna do some of the behaviors of the elements that make us. You're gonna see some of the behaviors in us. Some similar behaviors. Like metals are like men and they tend to lose things. Non-metals are like women and they tend to gain things.
I'm pretty on track with everything.
Well, if you look at the lifespans, Claire, women tend to live longer than men, right? So that's why if you're a guy, you want to make sure that you are interested in pursuing a relationship if you go that way, in which your significant other is wise with finances. Because a lot of people spend a lot of time accumulating wealth, and if you don't ever teach the other person how to manage that, then there could be problems with, a loss of those finances. Make sense? It happens. So women tend to outlive men. That's the point. If you didn't know that, you should know. All right. So there are some similarities. There are others as well. Men tend to trade. Men tend to have riskier behaviors too, like Into the Wild. If you read this book, this guy is constantly talking about men and how they've taken risky decisions, climbing various mountains and doing things that he doesn't talk. Not to say that women wouldn't do that, but I'm just saying that on average, men tend to be a little bit more riskier. Yeah.
Yeah, like just this morning, I was listening to Radii on the car, they were talking about these two guys that jumped off a mountain without parachutes and into an open door from a plane.
Yeah.
That's pretty risky. Right. So,
Intelligence.
right. So metals,
Hey guys, you want to jump into a plane?
they tend to trade electrons, which is more risky than sharing. You ever heard of no trade backs?
Yes.
Right. So, because sometimes people will make a trade and they're like, that was a bad trade. I should not have done that. Like you bought a car at a car lot and you're like, okay, that was a bad decision. And on the label it says, all sales final.
Yeah.
Right. So trades are a whole lot more risky than a share.
Sometimes you get.
You did what? What'd you say?
I traded like 4 Bakugan in 5th grade for this really big Bakugan.
Oh my goodness.
Yeah, you know what those are?
No.
They're like little ball toys that you roll and
That is so old.
And they pop up.
yeah.
Yeah.
I
Okay.
traded 4 small ones for one really big one, and then I started frying the bus because
Yeah.
Want to be over cold.
Oh, I traded some small ones for a big one. Best trade I ever made. I had the big dragon one.
Now, if you watch the stock market when it crashes, you'll see a lot of traders crying. And why are they crying?
Because they just
They
lost
lost a lot
millions
of
and
money.
millions of dollars.
Of money they borrowed. Most traders will borrow money and invest it.
Oh,
So
true.
they're living off of that return. So if it drops, they lost all the money they borrowed, and that's why they are kind of
Bitcoin is reaching its
distressed.
crazy amount. It's worth one Bitcoin is worth $10,000 right now.
Yeah, I've heard about that.
And 4 months ago, it was worth $600.
It's amazing.
It goes up and down, so you want to buy stuff when it goes all the way up, and you want to spend a lot of it
Oh,
before
yeah.
it goes back down.
Represents the picometer diameter right here. So I need somebody to read for us what says atomic radius, many properties,
What page?
187. How about Heather?
There's a book right under.
Many properties.
Deadline.
Many properties of the element.
152 represents picometers, which is a very small meter. And you wanted to organize this to where the larger balls, the largest one is at the bottom. So you pick out the largest one, and that should have been over here. That is the CS. They actually have the symbols on them for you. So they've kind of given you a little bit of a hint. There's helium, here's neon. So neon should have been over here. So they're kind of being a little bit nice to you. You could have looked at the periodic table in your book to reference this. You can see how she's got neon and sodium together. Now, students aren't always aware of the obvious, right? Have you seen, you ever went to that new place where you can go play Breakout? You ever heard of Breakout? Where you go into this room and you try to break out. And it's very difficult sometimes to break out because a lot of people don't observe the obvious. So they get stuck in the room. So it looks like on the internet. Louisville, Kentucky, Breakout. So, Ramsey, you said you broken out of there? It's pretty good. Ransom. What about you, Jamal? Have you broken out? You ever been? Yeah, I haven't been on it. Which elements on the periodic table are most abundant? Raise your hand. Zane?
Metals.
Right, the metals. What color are they in the periodic table?
Here are the blue.
Right, the blue. So you can see how they are very abundant. The metals. The largest radii diameter will be on the bottom left column, right here. Now, what does this number represent? 227 for potassium. It's the the radius for potassium, and that is 227 picometers. Anybody know what a picometer is? It is a 10 to the negative 12, like a dozen. 10 to the negative 12 meters. So it's very small. Now it's not as small as like Planck's constant, 10 to the negative 34, but it is small in the diameter. Picometer. Now, the smallest atom on your overhead up here is which atom? Yes, helium. Does everybody see helium up there at 31? It's interesting that helium is smaller in diameter than hydrogen. So would you expect hydrogen to have more or less energy than helium? Does hydrogen have more or less energy than helium? Hydrogen has more. If you light a match around hydrogen, it's pretty explosive. Right, so electrons are moving a little bit faster. It's got more energy. When it's pushed, it's going to release more energy when the electron goes closer to the nucleus. Examining the table of atomic radii, you'll see that comparing it to what we see here, you can see how there's a gradual increase in size. Now this is not correct here, but you can see how cesium is the largest sphere. Up here we go with then beryllium, then unknown 1. You can see how it gradually increases. The larger radii should be in this direction because you can see how the radii increases. Now this table that I showed you is just a mere pattern. When you're trying to do something, let's say new, you always want to look at nature first and notice if there are any patterns that you might be able to replicate. I don't know whether you're going to build a new assembly line. You might want to look at DNA and how it is manufactured. What are they doing to promote efficiency? Now your body is more efficient than what? Raise your hand. Let's say an automobile engine. Now your body is similar to an automobile engine in that it does what? How is your body similar to an automobile engine? How does it lose its energy? Starts with an H. Raise your hand. How does your body lose energy? Loses energy in. Are you poikilothermic or homeothermic? You're homeothermic. That means you lose energy by what? Losing heat. Yeah, so the loss of heat determines your efficiency. When you look at an automobile engine, when it's hot, that's gasoline that was wasted. Now I was talking to my uncle over the Thanksgiving break. He says 30% of new cars do not have what? 30% of new cars do not have this. What is it? Might know? New cars do not have a, starts with S. Two words, one starts with the S, the other one starts with the T. If you get a flat, that's a problem.
Spare tire.
Yeah, they don't have spare tires.
Silicon is also used to make prosthetics or in lifelike applications as shown in Figure 6.6. This introduction to the periodic table touches only the surface of its use. You can refer to the Elements Handbook at the end of your textbook to learn more about elements in the various groups.
Okay, the periodic table you see behind you was published in 1925. So the metalloids will be found right along this stairway. The important thing to note about 1925, Henry Deming published this, and he actually put the noble gases on the group over here to the far right, correction, to the far left. They call it the inert gases. On the current periodic table, they're to the far right. Is everybody clear? So this is kind of similar to what Jacob did on his table right here, where you see helium, neon, argon, and xenon, the noble gases, the inert gases. So this pattern is progress. If you remember the first table, 1869, correction, 1863, all the way to 1925, what is that? How many years is that?
That's a lot.
Well, 25 plus, let's see. Right, so 62 years of progress.
The outer limit of an electron cloud is defined as a spherical surface within which there is a 90% probability of finding an electron. To power this surface,
Electron configuration of AR4S2 and 3D10 4P1 gallium valence electrons are in the fourth energy level, and gallium is found in the fourth group.
Oh, go ahead, Ethan.
the energy
Of an electron cloud is defined as the spherical surface within which there is 90% probability of finding an electron. However, this surface does not exist in a physical way, as the outer surface of a golf ball does. Atomic size is defined by how closely an atom lies to a neighboring atom. Because the nature of the neighboring atom can vary from one substance to another, the size of the atom itself also tends to vary somewhat from substance to substance. For metals such as sodium, the atomic radius is defined as...
Can the radii of a single atom be determined? Raise your hand. Maddie? Yes? Why?
Because it's a single.
Okay. Josh?
No, because it can vary from sources.
You're close. What we just read, basically answer the question in what we just read. It says right here, however, this surface does not exist in a physical way as the outer surface of a golf ball. So basically, the atom doesn't have a surface to measure. So it's very difficult to measure it by itself. If you were to land a spaceship on the sun, it would sink because there's no real surface there. It's a gas star. So that's kind of what's going on with the atom. If you were to try to measure it by itself, it's going to be very difficult to do. And that's why you see these figure 6.10, 6.10 is showing you the atoms are together. That's how they're measuring the radii, because the surface is not like a golf ball. They're saying like a golf ball in here. It's not like a golf ball. So it's something you can relate to a little bit. Now, one last question. Up here, these numbers, like for lithium, it's 152, sodium 186. On page 187, they're showing PM. What is a PM? This goes back to chapter 2, if you remember. Trey, this goes back to chapter 2. PM. What does M stand for? Raise your hand. 5 points. 10 points. Raise your hand.
periodic measurement.
Close. What does the M stand for? 20 points. No. No. What?
Measure.
No.
Recall from chapter 5, the electron cloud surrounding the nucleus does not have a clearly defined edge. The outer limit of the electron cloud is